Thank you very much. Okay, can you hear me okay? Great. So yeah, let's get going. I'm really pleased to be here. It's my second time in Sweden, actually. My first time was in 1993. Went to a algorithmic and automated debugging workshop. It was my first paper down in Linköping. Yeah, so that was a lot of fun, and it's great to be back. So yeah, so I want to tell you about work that is about the automated generation of tests for programs using automated theorem provers, which are also known as SAT solvers or SMT solvers for Satisfiability Modulo Theories. And this is work that's done primarily by others. I've dabbled a little bit in this, but I think it's a work that's come of age, and as you'll see, I hope you get the idea there's not only interesting research in the area, but practical tools that are being applied in industry. So I have two lectures, and the first one is going to be an overview. So I'll give an overview of a quick overview of this idea of automated test generation and its applications. Then I'll talk about the technology that really makes automated test generation for programs go, and that's SAT solvers. And for those of you who don't know what a SAT solver is, don't worry about that, because we'll review that. And I will also show you the theorem prover Z3 that was developed by Leonardo de Mora and Nikolai Bjorna at Microsoft Research. And you can download that, and there's a Python interface to it. We can also play with it on the web. And then we'll talk about the primary idea, which is to reduce testing of programs to the problem of satisfiability. And we'll talk about a particular form of symbolic execution that does that reduction called dynamic symbolic execution. The second lecture, actually, I'm going to go into a program that you can download and play with, which is a very small symbolic executor, example of symbolic execution for Python, written in Python. So it's available on GitHub, and I just got it to pass all the regression tests last night. And it's a tiny little model that you can use to play around with to sort of understand what dynamic symbolic execution is all about. So lecture 2 is really going to be more of a deep dive into the guts of this implementation. It's quite small, so that you can see how this reduction of program testing to SAT solving works. And then I'm going to give you some exercise and extensions to work on. So I'm going to be here all the way till Thursday night, and I hope to be hacking on the symbolic executor with you, and maybe we can make it a little bit more robust than it is. So this should work pretty much on any platform. We've got Z3 for Linux, Mac OS, Windows, and Python's everywhere too. So I'll give you instructions later about how you can download and get things installed. Okay, so that's just overview of the two lectures. So what's this idea of automated test generation? So really more properly speaking, we're talking about white box test generation. So we're giving an open program, a program with a set of parameters. Think of a function in Python or C or Java or your favorite language. And what we would like to do is generate inputs to that program that will cover as many statements, branches, paths as possible. Really the goal here is to find bugs. So we would like to root out bugs in the program by taking existing inputs, running the program on them, but then finding new inputs. So typically in testing we develop test suites by hand. With automated test generation, we use the power of symbolic execution and the SAT solvers to complement our test cases with new test cases that can be derived by actually examining automatically the program structure. So that's the basic definition, and there are many applications of this idea. So I'm going to talk about two in the introduction. One is what's called white box file fuzzing. So in the area of security, a lot of times people can attack systems by sending you, say, a Word document or a PDF file that has been crafted in such a way to expose a buffer overflow in the application that would read that file. And that can happen because the application was written in C or any number of languages which have vulnerabilities such as buffer overflows. And if you open that file, then you're opening yourself to attack because the file can be carefully crafted, not just to overflow the buffer, but to put some payload in memory and then execute that code, take control of your system. And so how many have heard of the heartbleed bug? You heard about heartbleed? Yeah. So that was a buffer overflow, a read overflow. It didn't take control of the system, but it basically sent a lot of your server state back to anybody who did this heartbeat message, and you could read off cryptic passwords and all sorts of things. So file fuzzing is one way to try to cope with the mess that the C language gave us, and we are still working on that to this day. Another goal might be to actually do better testing up front than try to find bugs in these dusty deck programs after the fact. So another idea is, well, if I'm using unit tests or test-driven development, I could use a form of unit testing called parameterized unit testing to have the computer help generate new tests for me, and that's something that we've done with the Pex tool. So there are two tools from Microsoft that target these applications. One is called SAGE, which targets white box file fuzzing for security vulnerabilities, and another is called Pex. And SAGE is doing symbolic execution on x86, and Pex is doing it for .NET. And there are many, many more applications of this automated test generation, as we'll see. Okay, so let's talk a little bit about what SAGE does first, the area of security testing. So here's the idea. So you have a parser, and it's for some parser in Windows, which has been carefully called Media 1, but this was a real bug that SAGE found. And so fundamentally, this sort of idea of automated test generation, at least in the case of dynamic symbolic execution, you start with an existing input. So here, there's a seed file which contains nothing but 0 bytes. And we give it to this parser and execute the parser. And the parser is defensive. It's looking for special formats. So it's going to parse this and come back and most likely just fail to parse the file. But as a result, it will give up some information, such as, oh, it expected RIFF to be at the header of this file. And so SAGE explores the code to figure out that, oh, in order to get past the first check of the parser, it needs to include these 4 bytes, right? And so I'm not showing you the internals, but the effect is that you start with a second input. You start with seed 1, you get the generation 1 input automatically, which progresses a little further into the code, and then this sort of keeps going. So as you get deeper and deeper into the parser and the conditional checks, you're probing the branches of the program, which are telling you dependencies on the inputs, and you're crafting inputs to take branches that go new directions. And at some point, woohoo, success, there's actually a crashing test. So the idea is you're exploring a set of inputs, but examining the program's control flow, using that to determine new inputs that cause a new branch or a new statement to be executed. And then along the way, you're also doing things like checking for buffer overflow or looking for crashes. So this is SAGE. And here's sort of the idea of how that process was working on a much simpler parser. Okay, so this little function is taking a 4-byte array of input, and let's say there's something bad that can happen if the string bad exclamation mark happens. So if we get the string bad exclamation mark, then count will be equal to 3, actually it'll be equal to 4, and then this crash function will be called. So the way SAGE works is you start with some arbitrary input. Let's say you started with the input good. And you're going to execute the code on that input, but along the way, determine which direction each branch took, and create a symbolic constraint for each predicate. So fundamentally, we can think of there being 4 bytes and naming them I0, I1, I2, and I3. And so when this condition executes, it executes false. So that creates the constraint I0 not equal to B, right? Okay. And as we go through the path, we're comparing each input to the corresponding good, and we're going to see that none of the characters match, right? So at the end, we don't crash, but we get a path constraint. And you can think of this as a conjunction, saying that for that particular input, this was the constraints on the primary inputs. And so now the idea is we'd like to find a new input that would take us a different direction. So the way we can do that is we can pick one of the constraints and negate it. So let's do that. So we think of the first execution just came down the false branches, and that corresponded to the input good. Now we take the last constraint and we negate it. And we say, okay, I would now like to generate an input such that the last constraint, I3 is equal to exclamation mark. And the other 3 constraints remain the same. So that will potentially, well, give us the input goo exclamation mark, although a constraint solver could come up with other values for the first 3 bytes, right? So that would be a new input that we would get by taking this constraint and these 3 constraints. Is that clear? Okay, so the process of this automated test generation is to build this constraint system and then look for new inputs by essentially playing around with the constraint system. And so we can find, obviously, another way we could take them is we could take these 2 constraints, flip this one. And essentially, the idea is we'll take some prefix of the constraints, and then we'll take the last constraint after the prefix and negate it, which basically says, take us down the same path, but at some point, diverge off that path. So what we're doing essentially is for this one path that we recorded, exploring 4 possibilities, right? And in SAGE, they call that a generation 1 set of tests. So off that first execution input, we get now 4 new inputs, and then for each of those, we can repeat the process, right? And if there are loops in this, that makes it a little interesting, but generally this is the idea of how SAGE is trying to find these so-called inputs of death, inputs that will crash the program. Right. So fundamentally, there's a large search space, and even for finite programs, especially with conditional branches or procedure calls, you get an exponential search space, and here's the search tree, right, that you get by sort of exploring, here's like one path to good, and then here are the four generation 1 paths, and you can see all the branching we get. So the search space is quite large, and as with model checking or any sort of exhaustive testing strategy, you've got to deal with this space and search it in a smart way. Okay, so this tool has been used at Microsoft now for about 5 years, actually 6 years. So it's really the first big, large-scale automated tester for security testing. Since 2008, probably 400 machine years, SAGE just runs on all these parsers that we have. Actually, we have a cloud. We put SAGE in the cloud. We just keep running it, generating new tests. So you can think of it sort of like, you have all the black hats who are out there reverse engineering code, looking for exploits. We have our cloud. We're running SAGE against them in competition, trying to find the exploits before the hackers do. Although now SAGE has been so successful, if you go out, you'll find lots of people crafting their own SAGE-like tools. So it's an escalation of weaponry. Yeah.
If you want to do it small scale, then the initial path will be significant in reaching the interesting part of the code, right?
So by small scale, you mean starting with a small input?
No, what I mean is that we don't want to use a huge cloud, we just want to do it for our own software.
Oh, yes.
Then the initial path is very significant.
Oh, yes, the seed files make a tremendous difference. So it's you know, starting with all zeros might not be the best way. Like in that particular example, it was just to show that you could do that. However, in practice, you start with seed files that represent well-formed files that will get you deep into the parser, and then you explore the corner cases. So yeah, the initial seed files are very critical. So there's huge amounts of data about SAGE. There's actually an XIII paper, I can't remember, I think it was 2013, where they talk about all the bugs and things they found with Windows 7 and Windows 8. So this is an interesting graph. Let me go into this. So file fuzzing is not a new idea. People have done black box file fuzzing for a long time. And so for Windows 7, for 3 years of checking it, a number of bugs, I can't tell you how many, but you can see this amount was found with traditional techniques, which are black box techniques. Then there were some other techniques used as well, traditional testing. And then SAGE came in after the fact. And 1/3, if you count up just the total number of bugs, 1/3 of all the file fuzzing bugs found in Windows were found by SAGE. So you start with very simple techniques, they call them monkey testing, where you just throw random byte streams and you do all sorts of stuff, which is not looking inside the code, right? And then you do all the manual testing, and then you bring SAGE in after the fact, because it's pretty heavyweight. I mean, it's like a model checker, and it still finds in the end 1/3 of all the bugs. So that's very significant. And we're talking about, I mean, what's the cost of one of these bugs? Well, if people find an exploit, that could be millions of dollars of lost revenue. I mean, people pay, bug bounties for these bugs, these sort of exploits. So finding them early is a very good thing. So SAGE has saved lots of money for Microsoft, probably for our partners too. We do fuzzing on third-party applications as well. Primarily, we look at our own, but we've been looking at others. So that's SAGE. So SAGE is in use every day, primarily for binary file formats, as you saw before. Doing fuzzing for things like XML, C programs, other things that are more highly structured is another interesting research question. SAGE looks at the low-level sort of file formats that are binary. Okay. So any questions about that application? Okay. And there's plenty of papers you can find about SAGE, and I'm happy to chat with you more about that. Okay. So now here's another idea, which was pioneered by the Pex project. And this is parameterized unit testing. So in unit testing, you have a class under test. You want to test some of the methods. And so you'll craft inputs and test the method under test in a variety of ways. The idea of a parameterized unit test is again, a program that's open. So here we have an add test. It's going to take a list and some item. And the method under test is actually this method here. So the idea is we want to add an item to the list, and we're going to assume that we're given a non-null list. We're going to capture the count of the list into a variable, and then every good unit test ends with some assert. And so the idea is if I add an item to a list, regardless of its value, after the add successfully completes, the count has been increased by 1. Okay, now the code, we haven't looked inside, but the code of add may be fairly complex. Maybe this list is actually implemented with some sort of a complicated data structure. Who knows what it is? So we would like to generate interesting values now for these parameters. And this is quite a different, conceptually this is very similar to SAGE. But it's actually quite different in terms of the needs of the underlying SAT solver, because now we're talking about an object-oriented program with a class named list, And we've got our fuzzing tool, as it were, our test generation tool, actually has to create one of those lists, and perhaps several types and an integer. And so it's got to look inside the code and analyze an object-oriented program. Whereas with SAGE, we were looking at x86, fairly low level. That has its challenges. Here at this level, the PEX tool is looking at .NET code. But the idea is a neat one, and it's been demonstrated for several years with PEX that we can achieve after a tester creates a number of manual tests, unit tests, we can go there and increase coverage and increase the bug finding capability of the test suite using PEX. So as with SAGE, the seed files are very good, they help us get going, but we can use something like PEX to go further. And with PEX, we actually have a web interface, and we can take a look at one of the examples. Let's see that, if I have that right. Right, so here's an example of PEX. So here we have just a tiny trivial example, but just to show, it's a puzzle, so it's an open program that takes an array of integers, and it's going to throw an exception if it gets a non-empty, a non-null array whose length is greater than 0 and whose third element is some value. This is not a very hard one for PEX, but we can ask it, and it will go off and find a number of inputs. And so it finds the null. It finds the null value for V. It finds the empty array. It finds an array with one element, which actually is going to cause an index out of range exception here. Then it finds an array with enough elements so that the conditional check that's implicit on the array bounds does not fail, and then it finally finds the array that covers the exception. So this is showing you that that PEX is not only taking the conditional branches in the program into account to craft the input, it's also using the underlying runtime checks and the semantics of the language to do that. And PEX for Fun is available on the web. You can go there and play around with it. There's some very interesting things called coding duels there. But let me just show you another example. So here's another little example. What values of x and y solve this equation? So here we have nonlinear arithmetic, right? And so we're asking for values of x and y, that x and y are between 0 and 100, and they satisfy this equation, right? And so this is showing off the power of the SMT solver to solve arithmetic problems as well. Okay, so here's the equation solved one. If x is 37 and y is 4, we get to the console write line. So this sort of shows you very, very simply the power of PEX. It's doing something very similar to what I showed you with SAGE, except it's got to do it for all of the types in the .NET type system. Whereas SAGE works at the byte level, machine arithmetic. Here you're dealing with arrays, integers, collections, and classes. But essentially the same basic idea of white box testing and automated test generation. That doesn't look like a very good slide. There we go. Okay. So any questions? So those are the two applications. PEX is available also. Actually, SAGE is not available externally. It's used internally. It's our secret weapon. We keep it under wraps. But PEX you can get and download for Visual Studio, or you can play with it on the web. Okay. So yeah.
I probably missed it, but how does SAGE know the internals of the program?
Oh, right. Yes, I didn't say anything about that. But as we'll get to in the second lecture, any one of these tools has to have several capabilities. And one is to essentially trace the program at whatever level it is. So we have a whole tracing infrastructure, a virtual machine for x86 called TrueScan. So we actually trace an execution of an x86 program, and then we can re-execute that trace and reinterpret the machine instructions to build the formulas. With .NET, we do something very similar, except we don't trace it, we actually instrument the bytecode. And so while .NET is running, we're executing additional code to build symbolic expressions. In the next lecture, I'll show you how we do it for Python, which is essentially to overload, say, the definition of a Python integer to compute symbolic expressions as well as .NET. But you do need the ability to trace. Fundamentally, you need the ability to trace a program at some level of abstraction. So virtual machines can be done for that. You can use program instrumentation. The instrumentation we'll do for Python is at the level of abstract syntax trees. For .NET, we do it at the level of bytecode. That allows us to forget about the front end. So for Pex, you can run the tool on F# code, because it's, or C# generated code. Yeah. So here's the basic problem. If we look at what we've been talking about testing of a program, and the fundamental question, the challenge is given some statement in the program, is there an input that covers that statement? And for any interesting program, that's an undecidable question. So it seems like that's very hard. But as we'll see, SAT solvers are merely, the problem of satisfying assignments of Boolean programs only NP complete. So maybe if we reduce our goals for testing, perhaps we can do some reduction of a testing problem to a SAT problem. And we're going to have to give up some coverage. We're going to have to give up something, because in general, this problem of reachability of just a statement in a program is undecidable. But if we're just after bug finding, we can make some restrictions on the program, and then do a reduction of a program testing question to the problem, the simpler, only NP complete problem of SAT solving. Okay? So in order to understand how we're going to do this reduction, which is the primary way both SAGE and Pex work, we're going to have to understand a little bit about a SAT solver. So let's see. So I assume that everybody's familiar with the problem of Boolean satisfiability, propositional satisfiability. But how many people know how a SAT solver works? Oh wow. Okay. So this is going to be review for quite a few of you. But for those of you who don't know, I think it's good to define things. So we're going to have a propositional formula in conjunctive normal form, and here's a particular formula, phi, which is over the variables, the Boolean variables a, b, c, d, and e, and we're going to give this to an algorithm that's generically called DPLL for Davis, Putnam, Loveland, and who remembers the last L? There's another L, there's another one in there. Well, it started with Davis and Putnam. It was a resolution-based procedure, but it became a search-based procedure, I think, with Loveland. So the idea fundamentally, you can forget about this pure literal rule, is you're going to be doing a search. And so really the point here is you're going to pick some variable, and you're going to say, well, A is a Boolean variable, so let me just try true for A. And then what you do is you look at the implications of that rule. So if you have a clause that says A or B in your program, and now you decided to map A to false, let's say, now this clause has to be true in a satisfying assignment because it's in conjunctive normal form. So if you decided that A is false, then unit propagation implies that B must be true, right? So it's just basic deduction. So you select a decision variable, you make a decision one way or another, and you recurse. And when you recurse, you apply unit propagation to see what other variables values must be determined under the current assignment. And you do that when a clause becomes unit. A clause is unit if all its literals have been assigned values except for one. And then the last one The last literal you can identify. And if at any point that formula is unsat because one of the clauses is false, you say, oh, I made a bad choice, and you backtrack. Okay. And there's lots of fanciness now in backtracking, which I won't tell you about. There's something called non-chronological backtracking, and there's also something called lemma learning. And if I had more lectures, we'd talk about how you learn lemmas and all sorts of cool stuff. But this is the basic idea. It's very simple. You pick a variable, and which one you pick, that's the whole subject of PhD theses. Which variable do you pick? How do you pick its value? And then you explore the implications of picking the value. If you get sat, you're done. If you get unsat, you backtrack, and you try the other choice. Okay? So let's just take a look at that on our little example. So we might start with a tree, and at the top of the tree we decide for whatever reason to pick A false. So A false will mean this red dot, and when something becomes false, when the literal becomes false, it's in red. Okay, so now we don't have any units, right, because there's no unit clauses, okay. So we picked A false, so we pick another variable B, and we pick B to true. Now if we pick B to be true, then we get a unit clause here, right, because now A is false and not B is false, so E must be true. So E is implied to be true when we pick A false and B true, right, and therefore this clause is false. Oh no, wait, we have another unit clause. Right, also D must be true, right? Okay, so once we pick A to be false and B to be true, we get a conflict because it implies that E must be true and D must be true, so the clause not B or not D or not E is false, and so we've reached a conflict. Is that clear? I think I did that correctly. Okay, so now we backtrack. And I'm not going to talk about non-chronological backtracking. We're going to try now B false, and then we're going to not get the conflict there, but we're going to get another conflict. And now whatever way we go for C, we're going to get conflicts. So we'll backtrack up to the level of A, say what happens if A is true. Okay, and now if A is true and B is false, we actually get we'll get a solution. Okay, so this is the essential idea. We make choices, we explore the consequence of the choices, we get conflicts, we backtrack, we eventually get a solution. Okay, so SAT solvers have been around for a while. Let's just take a look at how we do this in Z3. So again, I encourage people to download Z3 and I think we can make that a little larger. If I could remember where the font size was. Okay, here we go. That might be better. Okay, so here's how we solve that problem using Z3. Once we've loaded it in, we import from the Z3 module, we create a solver, and actually it figures out what type of solver to use. Oh, can you not see the left side? Okay, and I should probably turn off my email since I'm connected to the network now. Okay, is that better? Okay. Right, so we basically tell Z3, create a solver. We call a function in Z3 to say, give me 5 Boolean variables. These are now A, B, C, and D in the Python namespace. And now we create phi as just a list of ors. So here we say, here's one clause or of A, or of A, or not B, or D. And a list, we think of a list as just conjunction. So the conjunction here is implicit. We take that set of expressions, we assert them all, which is essentially saying we want them all to be satisfied. Here we check the result using Z3. If it's sat, we print the model, which is the satisfying solution. And so we just do that. Whoa, that's really tiny now. Try that. 16 by 12. Ooh. That is not happening. How about, how about that? That's a little better. Okay. So we can say Python cnf.py, and it comes back with values of A, true, and B, false, and it's a complete assignment. So fundamentally, that's a SAT solver. It's pretty easy, and these days you can find many varieties. For 20 years now, there's been a SAT competition held every year where people create new SAT solvers, and they go head to head on a huge set of benchmarks. They're always improving things. But at the level of things like SAGE, we don't want to deal with single bits because we've essentially got machine words. So we'd like to do bit vector or machine level arithmetic. And so the sort of questions we're asking are not satisfiability levels at the level of Boolean variables, but are more questions like this. So if X and Y are 32-bit integers, maybe they're signed or unsigned, is this equation valid? Is X greater than 0 and Y greater than 0 and Z equal X plus Y imply that Z is greater than 0? Okay, and so the way that bit vector decision procedures work then is to essentially what's called bitblast them. So just as in an ALU or a machine you create circuits to implement addition and comparison, you can do the same thing with bit vectors and addition operations. You compile them down into SAT. And so fundamentally, at the most naive level, you can encode these questions of bit vector satisfiability into propositional logic by encoding n-bit integers using n propositional variables. Now in practice, there's lots of specialized algorithms for bit vectors that do a lot of pre-processing before, but in the end, this idea of bit blasting, compiling to SAT, is essentially what's happening. And so that's just analogy for what we're going to do in the larger sense, where if you have finite words, you can compile them into SAT. Well, if you have a finite program path accessing finite words, you can take that program path and compile it into SAT and also use it for test generation. So what we're doing here is we're scaling up from the single level of a bit to essentially bit vectors to words, and then at some point we're going to have to expand our scope to programs. So the idea is we're going to encode arithmetic operations using hardware circuits, and we're going to create programs to encode these expressions using SAT solvers. So we're going to encode equality between two bits using this formula, right? So P implies Q if P and Q are equal, if P implies Q and Q implies P, and then we can encode equality as just the conjunction, the equality of two bit vectors of length n as just a conjunction of equalities between the bits, right? And if we want to do addition, then we use our friend XOR. So we're going to compute X plus Y. We have a P XOR Q is defined as not P equal to Q. And XOR, as you know, is the 1-bit adder. So here's P and Q. Here's XOR, which is the add of the two, and P and Q represents the carry bit. Okay, so again, we're reducing everything to SAT. Here's how we encode a 1-bit full adder with 3 inputs. So we're going to have X and Y plus a carry bit coming in and 2 bits coming out. And then for an n-bit adder, we can just do the carry propagation. So here we get the carry, the result for the first bit and the carry for the first bit. Now the result for the second bit is the XOR of X2 and Y2 plus the carry bit as well. So it's fairly straightforward. You're going to get a finite, again, you're going to get a finite formula and blast it to the SAT solver. So in terms of how we would define this in Python here, we simply have, if we have x, y, and cn coming in for a single bit, then we can return the pair, which is the XOR of x, y, and cn, and then, as you saw, the equation there. So we can program directly against the SAT solver, creating the formulas given the input formulas. Or, since Z3 has a bit vector decision procedure, we can just do the following. So we don't have to encode it ourselves. We can just say to Z3, okay, give me 2 bit vectors, A and B, of length 8, and then assert this sequence of expressions. So A greater than 0, and B greater than 0, and A plus B less than 20, and A minus B less than 5. And notice we're using just Python expressions here. So A and B are bit vector types from Z3, and all the operators have been overloaded. So it's really easy now. You can imagine this almost looks like a program, right? Because we're typing in Python, but essentially we're creating Z3 expressions and then doing the checking. So we're almost there. We're almost done with lecture 2, right? Which is how do I take a program and compile it to a SAT solver? It's just here I've shown you that the Python overloading makes it very easy. So here we can go and say Python on what was that? Add py, and it tells us b equal 13 and a equal 3. So plug in b equal 13 and a equal 3 there, and I think yeah, the equations are satisfied. So that's sort of SAT solving 101, very simply. The SAT solvers are there, they're plentiful, there's nice programmatic interfaces to them, and then on top of the SAT solvers, people have built other decision procedures. This is actually then if you want to do symbolic execution for things like Pex and go beyond machine words, then there's a whole other set of theories and things like sets and maps and lists and floating point. You might want to do that too. But here, for the purpose of these 2 lectures, we'll be content just to stay with bit vectors. Okay, so yeah, as an exercise, you might, for kicks, take the Z3 Python interface, just, figure out how you reduce to SAT. It's fun exercise for multiplication or signed or unsigned comparison, but you could just say, I don't want to do that, just let Z3 do it for me, because it has the bit vector decision procedures. Okay, so coming back to this picture then. So we're a little bit more familiar now with what the SAT solver is going to do. So the question is, how do we reduce the question of testing a program into SAT? And the answer is very simple. So we're going to bound everything. So people have heard of bounded model checking, finite exploration. So the problems with programs are they're unbounded in particular sense. You can have a while loop. You don't know how many times it goes around. You can have recursion. You have an unknown data structure. You don't know its size. So this is quite different than adding finite length bit vectors. So what's the hope? Well, the hope is to just define the hard problem away by then doing bounding. So the first thing we're going to do is, instead of dealing with programs, we're going to deal with paths through programs. So we're not going to deal with a whole program with all the loops and everything. We're going to explore one path at a time through the program, and that path is going to have bounded length. Now, of course, there's a huge number of paths. So the first thing we're going to do is we're going to give up sort of some notion of completeness. We're not after proofs, although if I had more time, we'd talk about how you might get to proofs. But we're going to select some set of paths from the program, a finite set, and then explore those paths. And we're going to put a cutoff on the length of the path. So this means we're doing now explicit enumeration, generally, of the program paths. We're going to bound the number of the paths we explore. But even then, we have to bound the length of a path. So what this generally means is bounding the input size or path length. So for example, with SAGE, it's very, very useful to start with small seed files. Some people start the SAGE file fuzzer with a megabyte file. Well, a megabyte file translates into a very long path with a lot of constraints. It turns out that a lot of bug finding activities are much more effective if you start with small seeds and then explore off of those. So this is the essential idea. We're going to bound everything, and because of that bounded exploration, we're able then to convert a finite program path to a finite logic formula, and then do the SAT solver to tell us interesting things. And in particular, we're not going to take an existing program path, but we're going to take some program path that's similar to one we've seen execute, then say, well, is this program path up to this point, but going this different way? Is that formula satisfiable? So we've already explored some path. What we want to do is explore the neighborhood of paths around that and achieve greater coverage. Okay. Right, so this idea is known as symbolic execution. It's been around for actually a very long time. So if you want to sort of do static analysis of programs, one way to think about it is start execution from the initial state with a symbolic value for each input. So some unknown for each integer, or some unknown for each byte in a byte array. And then as you march forward in your program, your operations like x plus y are now working not over concrete values for those variables, but symbolic counterparts. So you're, rather than saying, oh, x plus y is 5 because x is 2 and y is 3, you're going to actually build an expression saying x plus y, where x is the initial value of x and y is the initial value of y. And then when you get to a branch, now you have some interesting possibilities. You have a predicate that you're going to evaluate in a symbolic state, and it could go either true or false depending on the values of the initial variables. So essentially you're going to fork execution for each feasible evaluation. So C here represents the symbolic state that you've built up so far in terms of the existing variables in your program. Now when you get to a predicate P, you're going to essentially say, okay, under the current state or the current path condition that got me to this point, there's two possibilities. One in where I can join P to the current path condition, and one where I can join not P. And so this is the effect of branching and then exploring the alternatives. And of course, this is where you start to get a blow up. And so for each path that you traverse as you're going through the program, you get an accumulated path condition. And then at for each of those paths, you want to know, well, is this set of path conditions, is this set of conditions along this path, is it satisfiable? Because you might have chosen a path wrong such that the conjunction of the constraints is unsatisfiable, which is a proof that there's no input that takes you down this path. That's valuable. But in the case of symbolic execution with no seed input, you're making guesses, right? It's just like a SAT solver. Right? So you're making guesses about the branch directions in your program. That's just like guessing values for Boolean variables, and you might get it wrong. So when you're doing this sort of symbolic execution, you're going to use the theorem prover to say, is this set of constraints satisfiable? And it might say no, and then you have to backtrack, just like in a SAT solver. So this goes all the way back to James King, 76. So theorem provers, automated theorem provers, the idea has been around for a long time. And this idea of symbolic execution and test generation has been around, well, almost 40 years now. So there's really nothing new under the sun. It's just that our machines are a lot more powerful now. And we've had some modest algorithmic improvements as well. Okay, so I think you probably have the idea already, but let's just go into it a little bit more. So if I have a program here, although this is a finite program, so you can see the reduction pretty straightforwardly. So we're going to say, okay, we have an open program we want to symbolically execute, which is the max of 4 integers, and we're going to do that by first doing the max of AB, then the max CD, and then taking the max of those. And then the max function is over here on the right-hand side. So as we go through this program symbolically, the first branch we would get to would be essentially x less than or equal to y, where x and y are instantiated to a and b. And so we get a symbolic execution tree here. And this is the key idea of King, is that you're going to explore this tree where choosing a less than b true or a less than b false. And as you do that, you're essentially traversing the program and encountering these different conditions. Now, this program is relatively simple because there are no assignment statements in this program, explicit ones. So we're just, our symbolic inputs are essentially these 4 variables, and all we're doing is comparisons with them. But as you see, we get, not surprisingly, 8 execution paths here, right? And at each of the leaves, there's an assignment to values that makes the condition along those paths true. So in this particular example, there are no infeasible or unsatisfiable constraints, I believe. Right, everything's satisfiable. But so that's the very basic idea of King, was that you could essentially think of exploring a program just like a SAT solver, where when you get to the predicate, you're making a decision, true or false, and then at the leaves, then you call the theorem prover to say, is this accumulation of constraints satisfiable? And then making a call to get an input. Okay. So any questions about that? Oh, do you have some water? Okay, it's a really light water. Oh yeah. So exponential is key in everything to do with, model checking, whether it's of state machines or explicit enumeration of program paths. So yeah, so we'll get to the exponential, and clearly you need to have, techniques for taming it. For procedure calls, it's sort of well known. We compute procedure summaries. That is, if we call a procedure multiple times, we would like to avoid reanalyzing the procedure over and over again. But even within a single procedure, there could be complicated control flow, which a linear program can have an exponential number of paths. You just make n branches, n if then else branches. So you would like to have some way of also countering that exponential explosion. And there's something known as property-directed reachability. If I have time, I'll talk a little bit about it, but it's good to have a goal. So one of the things I haven't said about this testing so far is, it's sort of blind. I mean, what is it you're trying to go after, right? It just says, here's another predicate, let me explore that. But if you have a goal, if there's a particular assertion, like you're focused on an assertion, you want to say, is there a path for which this assertion fails? If you have a goal that you're after, you can use that goal to prune the search space. It's not to say you're going to get rid of the exponential, but you're going to hopefully reduce things. So this idea of property-guided reachability is a key idea. Although a lot of these search procedures that I'm going to explain, like Pex and SAGE, they really don't really build that in. So that's something that is I think for future work. But there are good techniques for doing that now. It's something called lazy annotation by Ken McMillan. Okay. All right, so this is the basic idea then. So symbolic execution of the program is like the SAT solver choosing values for Boolean variables. Of course, the reality is the things you're choosing over are predicates over program state variables, which could be integers, lists, arrays. So you're not in the Boolean domain anymore. But there's still a number of problems to make this more effective. One is code that's hard to analyze, and we'll spend some time talking about that. The second is this problem of path explosion. Even for very small, simple programs, you can get an explosion of paths. Obviously, if you have while loops, you've got unbounded, so you've got to have some techniques for doing that. But even acyclic programs with procedure calls, if you have a procedure being called from many places, you can have an easily exponential explosion that way. The other thing that makes it particularly difficult is the environment. So we've looked at easy programs so far, like this max function, which just takes some integers. But what if your program is is a client-server program communicating over sockets, or it's accessing a database that has some state and you're doing updates to it. I mean, how do you do symbolic execution when the environment is much more complex? And so there are people who've looked at things like symbolic execution with databases. And I think our next speaker, I don't know if our next speaker's here, but very good. What about multi-threading, right? So what if you have a concurrent program, right? And so now you have not just a single thread of execution, but you have multiple threads of execution, right? So there's the environment defines essentially the inputs to your program under test, and if that environment is complex, thank you. Thank you very much. If that environment is complex, it's going to become harder and harder to do symbolic execution. We're great. Okay. So I want to talk about the hard to analyze code. So, okay. So Patrice Gaffron, let me see, 2005, he was working at Bell Labs. It's before I hired him into Microsoft Research, where he worked on SAGE. But he came up with this idea of directed automated randomized testing, which is now known as concolic or dynamic symbolic execution. And his idea was the following. If you have this obscure function that you want to symbolically analyze or execute, and it takes integers x and y, and then calls some really tricky function complex. Now, what is that tricky function? It's a cryptographic function. It's a virtual function or a function pointer. You don't know what it resolves to. It calls the a kernel module, and you don't have visibility into the code. I mean, there's always some code that if you're doing just pure static approach, you get to that complex call, and you're like, I have no idea how to analyze this. So if you're trying to do this reduction to SAT, you're going to at some point come across some piece of code that you can't reduce to a SAT formula, right? It's just going to happen, right? So it may be very hard to it may be very hard to statically generate values for x and y that satisfy x equal complex y. But here's the very simple idea that Patrice and colleagues, Niels Klarlund and Kaushik Sen, came up with in 2005. And I've already shown you the idea here. Well, instead of just trying to statically analyze that code like King did with symbolic execution, why not just start with random numbers for x and y, like 33 and 42, right? And just execute the program, right? And so you're going to execute it both concretely and symbolically. And when you do this, you're going to find that the complex function on y equal 42 returns 567. And you're going to substitute the value x of 33 here. And of course, they're not equal. Big surprise. You just guessed values for x and y at random, right? So that constraint was too complex to solve statically, but dynamically, you just run the complex function. And then you say, well, let me not worry about generating a value for y, right? Because I've just picked one, and I know what the result of the complex function is on that. And so now let me just solve for x equal to that value. So instead of trying to get complete coverage of all values of x and y, you just say, look, whenever I run into anything that's too hard for me to do symbolically, I'll just use the concrete value. And this is such a simple idea, but it's so powerful because it basically says, look, you've got virtual functions, you've got calls to the kernel, you've got all these other things. Whenever you can't do a symbolic representation, just use the concrete value. And for testing, that's really fine because you're just losing coverage. It just means there are other value combinations that you're not going to explore. But the important thing is you don't give up. It allows you to make progress. So this was the very simple idea, and it really sort of takes you out of this very complex space into one where you can sort of keep making progress. And so this idea, which is known by Dart, was also named later by Kaushik Sen concolic execution, which is a nice pun on combining concrete and symbolic. And then I think also and known here, dynamic symbolic execution. So instead of symbolically executing a program without any inputs, like King was proposing, first run the program on some input. That's going to solve a whole bunch of problems for you. It's going to take you deep into the program. It's going to resolve virtual function calls. And then you're going to trace that program execution to record the concrete values and build the symbolic along the way. And so the benefit of that is you don't have to worry about whether that path is feasible or satisfiable. You're running the program, so you know you've got one good path. And now you've got that seed path, now you can start exploring off of it. And and wherever your SMT or theorem prover can't represent something like a virtual function call or an object hierarchy graph, you just say, look, for things that I don't know how to compile into SAT, I just execute it and I lose coverage. Okay? Such a simple idea, but really it's what's made, I think, SAT solvers plus this idea is really the core of dynamic symbolic execution.
Can this lead to a path divergence from one to another? This simplification.
Say again?
This simplification, can it lead to a path divergence? For example, if you simplify the complex function and it has another argument, let's say x,
Yeah.
it can predict the path that this will be true and maybe it will not if you substitute this value.
Right. So your question is, well, what if complex is a function of several variables, and one of them includes x? Right. So what you might be able to do is go inside the complex function and find that you can still run a lot of parts and maybe not keep x and keep x symbolic. But maybe at some point you'll decide you're going to concretize x. And then basically you've lost exploration, right? So I don't think it's divergence, it's a loss of coverage at least. But maybe we can go into that in more detail on paper. There might be, so the question is, do you, yeah, I think you only lose coverage in the sense that there are certain value combinations you won't get, but divergence is an interesting question. So divergence, so a problem, well, let's define what divergence is. So my understanding of divergence is you have a constraint system and you think you have a path you want to go down, and now the SAT solver tells you some values, and now you execute and you go a completely different way. To me, that's divergence, right? You thought that the values, in that sense, you have, your constraint system is sort of incorrect. So yeah, we should go into that. I'm not sure. I think there should be some theorem for concolic that says it's under approximation, but you're saying, yeah, there may be divergence as well. So divergence can happen, well, I mean, one problem is the SAT solver, even though it's theoretically complete, might time out, right? So one way you have divergence is, just bugs. You have the wrong formulas, right? And so you're solving a system of equations that doesn't really represent the program semantics. Okay, we should think about that more.
But there is another sense of divergence. I don't know whether that's what he's referring to. It means that the program engages in an infinite loop without.
Yeah. Oh no. So that divergence is always here. I mean, we always have if you meant by sort of non-termination, if divergence, yes, that's the more classic definition. This is generally the only sort of program for which, is we're always in this problem of this sort of technique. Just, you give it as much time as it wants, it's going to have another path to explore. For the little programs we look at, it'll terminate because they don't have loops. Okay. How are we doing on time, by the way?
Maybe 5 more minutes.
Oh, okay. Okay, good. Yep. Right. And here's the example of the function you saw before that we did live, the cover me function. So this is in context of Pex, so dynamic symbolic execution. If we want to start with the cover me function, we just say, oh, A is the null array. It's the null pointer. And the runtime comes back and says, oh, there was a choice. Either A was null or not null, and you took we observed A equal null. So let's negate that constraint and solve for A not null. And when we do that, we get the empty array. So it's now a non-null array, but it's empty. And so we make a little progress. We make it past this first check, right? And we make it to the second check. And now, is the length of the array greater than 0? Well, for the empty array, that's false because it's 0. And so we go back and we get a new condition. And that condition says, well, can you give me a non-null array where the length is greater than 0 now? And so we come back and say, hey, we're lazy. How about just one element in the array, right? And so this goes on and on as we go deeper into the program. So as long as there are more conditionals to cover, we make more progress, we refine the input, but we always start with an input that allows us to run the program, okay? Right, and so on. Right, so this is the very simple idea of symbolic execution. We essentially start with the formula F, think of that as false, that just basically says, I haven't found any paths yet, or any inputs. And then we say, okay, given that formula, find an input I that's in the negation of F. So if F is false, that just says, find any input. So if F is false, then the negation is true. It just says, give me any values, right? So we pick just some values for the inputs, and we then execute the program on the input. And as it goes along, we record this path condition, which is essentially this conjunction of constraints in terms of those primary inputs. Okay. Now what we do is we simply just say, hey, I have a new path. Let me add that path to my set, which in terms of the formula just says, take that conjunction and disjoin it with the existing set of paths. And so now the next time around, the idea is the negation will say, don't give me one of the paths I already covered. Give me something new, right? So this is basically it for dynamic symbolic execution, right? Give me a random input, solve for the negation, execute, record the path condition, go on. If you have a bunch of seed files, then don't start with a random input, just start with a bunch of seed files, right? But this is in the simplest sort of formulation what dynamic symbolic execution is going after. Now, we're going to go in the next lecture into the engineering, how we actually do this. But let's just say it's been very successful. It's been done for many environments in many types of languages. It's been done for C, Java, x86, .NET. People have used all sorts of different solvers for linear, nonlinear arithmetic, bit vectors versus God's integers, and the natural numbers, say, concrete heaps, symbolic heaps, floating point values, and there's a whole ton of different types of implementations, starting with Dart from Bell Labs and the Qt work to things called XIII, Vigilante, SAGE, Yogi, Pex. There's just a huge amount of work in the area. Whoa! Oh, that's from the Pex guys. And if you want to play with it on the web, I already showed you how to do that, so you don't need any tools installed. Just go to pexforfun.com and play around. One of the really cool things on Pex for Fun is the idea of a coding duel. So on a server, we have stashed away a whole bunch of programs, and they're programs that compute weird functions. And then you're given a program that is just a template. It just says, here's an array as input, here's an integer as output. What is the secret? That's the interface of the secret program. And then please guess the secret program. So what you do is you fill in some code and you send it to the server. The server combines the secret program with your program and asks the question, is there a distinguishing input? Is there some input such that the output of the two programs is different? And again, program equivalence undecidable, but you finitize it the way Pex does, and it generally is a very good counterexample finder. So it will come back to you and say, oh, your program differs from the secret program in these ways. And then it becomes sort of like a a number guessing game, or where you have a sequence. Like, what is this sequence? And you have to refine your program. So it's actually been quite interesting as a game. So just to recap then what you've seen so far, test generation using SAT solvers, choose an arbitrary input, get an execution path, add to the set of known paths, then do some negation, or say, give me something new. Ask the constraint solver to solve a variety of the path constraints, a variation to find a new input. And the reduction of finite program paths to SAT solvers mean we take this hard problem of undecidability, reachability, and we make progress. So we find new inputs that cover more of the program and hopefully give us bugs. In practice, very effective. I have a bunch of references from the King Classic down through the ages for you to look at if you want to dive into more. So that's the first lecture.